Okay, hi everyone. I'm Tsvi. I'm the general manager of the NEC Corporation Research Center in Herzliya. I established this center slightly over 2.5 years ago. We're about 30 people right now, mostly researchers, and we're growing. So anyone interested is welcome to contact me or one of our people in the crowd and ask for more details. But today I'll try to give half of this session will be quite technical. No equations, but some concepts which I'll try to explain to the best of my ability that are deeply technical. We're going to talk about explainability, and that's why we have this MAGA modified into MAXA hat. Explainability is a big thing right now in discussions. We're going to talk about some practical reasons why it's not going away, why you actually need it to deploy in the real world, and how to do it, which is kind of sounds like an ambiguous thing, but actually we have found some rather well-defined definitions for it. So, I assume the crowd here uses AI, maybe researchers AI. So the reason we're all talking about AI so much in the last 8 years is really two things. The giant success of recommendation engines in digital marketing, also known as the internet giants, and the success in image and speech recognition in the academic world. These were really two major shifts which made people realize you can actually apply this and make money from it or do things you didn't think possible in the academic sense before. And everything since has been shaped by these two. And that's very important. Why? Because, by the way, before I go about that and we talk about explainability, I have one question. I wonder, you know that people say now that ImageNet, people here know what ImageNet is? Yeah. So you know that they say in the recent years, ImageNet classification became better than people. You're aware of that, right? How many of you think that's really true? Okay. And of the few that do you think that are you willing to make a bet that now we will take out a camera and walk out in the field or outside this hall, and you will be using ImageNet and I will be using myself in a classifier? Do you think you'll win? You're not sure. We're not open. Let me tell you, you will lose terribly. It's a lie. Okay, it's an academically accepted lie in some sense, but it's a lie. Don't trust any ImageNet to do better than you. You will fail. And there's reasons. That's where we come to explainability. Okay, so as I said, on the commercial world, which is always the driver, the big companies which are ad companies, digital advertising. By the way, do you know how do you identify that a company is a digital advertising company? They never say that. They say they're here to make the world a better place, they have a colorful logo, they do Wi-Fi in Africa, they help children. All the money comes from advertising, 99.9%. If it was a scientific experiment, it would be considered total success. Or they make social networks, which I use a lot, just like you guys do, okay? It's not about advertising. But the money which pays for all of that, including the PR, is from one thing and one thing only, that they're able to predict better than others what you may click on, how you may respond, how you may react, or what to sell you. And that's true for all the big recommendation engines. Movies, products, doesn't matter. Now, okay, no one argues with success, least of all in the US. Money is money, and they have a colorful logo and everything. But in the last few years, people started to realize that maybe if it's just about accuracy, that's fine if you're doing stock trading, but maybe you have issues of bias or explaining why some people never got this really lucrative offer for a product or a flight. So at first, about a year ago, all the major corporations making money from this said, it's impossible to explain, it's a stupid question, we don't know how to do it. And then the government said, well, I don't like this tone of voice. So they had a discussion and feelings, and suddenly they feel differently about it, especially because they want to remain in business. So I'm not endorsing, by the way, this kind of book or anything. The only thing I wanted to make everyone realize is that the game where you say, I only care about accuracy, I don't need to explain it, is over. In some areas faster than others, but it's over. And it's not going back. Mobility. Okay, now that's a different case, right? Because I had to drive here because the Israeli railway system and the interaction with the taxis is not so good, okay? But I hate driving, especially in Israel. And we all would like, or most of us would like a machine to drive for us. The acceptance threshold, first of all, for this to happen is high. You have to be way better than humans for this, average humans, for this to take place. But that's still accuracy. But also there's the issue of stability and compliance. Compliance is the government way of saying, we want to get involved and see what you're doing, okay? Stability is very important. It's a valid question. Many people like me who don't like driving say, oh, come on, if it's 10 times more reliable than people, just replace. Who cares? I mean, like, yes, you will still get some mistakes. Who cares? Well, actually, that's not true. Because what happens, since you don't understand the system, what happens if you find out that when there's a hailstorm, which we don't have many in Israel, but we do, what happens if there's suddenly a hailstorm and no one took that into account when training the systems, and suddenly in one day you have 1,000 deaths? Ooh, what are you going to say? I didn't think about that? So accuracy is a very dangerous term. Accuracy is measured on what you know to test for, the environments you know to test for. When we talk about stability, we definitely want your car. I mean, you don't want your tires to work only when it's 30 psi, right? I mean, you should keep it at 25 or 30 psi, but if they're 50, you still don't want them to explode. That's the way engineering is done. That's the way society is built. You have area where you have the best performance, but you have a much, much wider area where things should still survive. And the problem is that some of these deep networks, we don't know if they'll survive once you increase the enclosure, okay? So you have the issue of stability and compliance, and that's why all the companies doing any kind of ADAS or autonomous vehicles development are thinking very much about that. It's not just compliance in the sense, okay, we have to sit in this boring meeting and hear some people do some lecture us about things we know better than them. You really have to think about it. How do you test that your system is stable? Okay? You did 50 tests in a hailstorm. Sounds good to me. Is it good enough or not? We don't know, okay? When we built planes, we learned how to build planes, we know now what tests you should do to the wing or to the fuselage, and it will work. And usually we get it right. But we don't know what exactly and how much you should test a neural network with 1,000 layers based on an amazing algorithm published 4 months ago. Wow, really solid. Right? And maybe in the GitHub there's some mistakes, right? So maybe actually you're not running what you thought you ran. So it's a problem. Medical diagnostics. Okay, I think here it's, some people which are much smarter than me said maybe soon radiologists are going to be replaced or doctors are going to be replaced. We work with hospitals, okay, and they tell us, and I know people like Dr. Eric Topol, if you know him, people who advise the UK government and the US government, and they already get asked by young people, should I enter radiology or become an MD because maybe I'll be replaced? I don't think there's a reason for concern. The nature of the work may change, but they're not going anywhere soon, okay? And of course, in these areas, explainability and stability are more important than even accuracy. Of course, the accuracy has to be good, otherwise no one would use it, but it's not enough. I will give some concrete examples of research where people trained models and it worked really nice in one setting, but they were clever and careful enough to test them in another setting before using them, and they didn't work well at all. They were terrible, actually. Explainability is also important when you're, a good example which I'll discuss later in more detail is lung CTs, okay? You do a lung CT for a person, especially smokers or people where you feel there might be the onset of some kind of cancer or something else, and you find something that you don't like. And it happens all the time, by the way. Most of you are healthy and will never have cancer in their lungs. May all of you stay healthy. And if you'll go and have a CT, some things might be found. And then there's the dilemma. Do I take it out, which is basically, or do a biopsy, or don't I? And the risks of a biopsy are not zero, especially if you're old and not so healthy. Quite a few people can get complications because of that. So to say the AI said I should do a biopsy, that's never going to fly. Not only in Israel, not only in the world, it's not going to fly in India, it's not going to fly anywhere. No one's even considering doing that. Don't believe the hype, okay? A professional will have to look and try to understand why it said that, or look at the image and make their own decision. It's still going to be useful for a lot of stuff, but not for everything. Okay, so what are really people, now let's get a little more technical. What are the people really, if you said, okay, let's not talk about, you're afraid of voodoo, but what are you concerned about? So there's the issue of potential ROC, receiver operator curve deterioration, meaning you measured it in the lab or in your hospital or in your test ground, and it was X, but you get to some other place and it's not X, it's actually much worse. And of course, you will only realize that way too late, right? Because it takes a lot of measurements and a lot of time to get your ROC. So frankly, you can't do that, right? When a hospital buys a CT machine, basically it expects to turn it on, and there's a few dials and a few things, and if that's okay, it expects it to work just like it did in somewhere else. If it's not, it's a big problem. By the way, across the hall, there's a much smarter guy than me called David. He works for IBM, and his company, which is very well known in AI, is saying that as well. Confidence in AI, and that's because they actually do projects. They don't publish CVPR, they do, but they have to actually sell that to someone or to convince them to use it in the real life. Explainability and transparency, that's the only way to go. So, stability. Let's do some practical examples which we in our labs encounter all the time and have to solve. So, for example, in object detection, you have all those amazing papers, and really, the academic work is amazing. We use it. We're not smarter than those people. We study from them. But they do pose estimation and cool stuff, and they take pictures indoor in the MIT lab, and it works great. But now we want to use it, and it's outdoor. This is Ashdod City, the central city hall, the square, city square next to the hall, and there's people there, and the camera looks at very different angles, and you have sunlight, which in Israel is very harsh, so the contrast is very bad, and that looks nothing like that. So you wonder, will it work as well there? Well, the answer is no, and you have to retrain it. But anyway, the question is valid. No, it's not going to work like it worked in the lab. Or you apply ImageNet, which was trained on perfect images used for advertising in the internet, taken by professional photographers with high-end Canons and good lighting and good centering, and you apply it anywhere else, and, well, what could you expect? I mean, object recognition. Maybe you've never seen, when you trained your model, a double-decker bus or a tandem bike. That's a problem. And in NLP, that's a very good recent result just from this month. People with the best of intentions and good skills tried an NLP model to do some analysis on oncologist reports, which are, by the way, very, very complex documents. You read an oncology treatment report, you understand why an MD has to be really smart. It's hard, okay? So they trained it on their system, and it worked very, very well. And then they use it on a different hospital, not a third world hospital, just the only crime of that hospital is that it's in Kentucky, okay? And the results were terrible. Why? Because, can you guess? Well, maybe the doctors in Kentucky are not the same guys as the guys in Seattle, so when they write the report, they use slightly different phrases and sentence building. That's what people do. Wow, who would have thought? Very happy, no one tried to deploy this just because there was a paper that it's good. Another problem is waiting. When you do research, you tend to treat all errors or mistakes with the same severity, but real life is different. One example which we encountered, and we all, I mean, I've encountered it in other industries in the past. If the mistake seems very silly, people attach much greater weight to it, okay? So when you do lung CT, lungs are super complex, and they're different. There's not two people. You could use it as biometric. Your lungs are really unique to you. And there's a lot of things that can make the system, make it hard to distinguish between a nodule, which might be cancerous, or something else. And you can make a lot of mistakes, and they'll forgive you, because they make mistakes as well. But suddenly, the machine says this perfectly looking blood vessel is a nodule, and they get really upset. Even if you do it only once per scan, which is really not meaningful for the workflow, they lose trust in your system. They say, if it makes such silly mistakes, maybe something's wrong. Another problem is distribution of errors. That's an example, actually, of an adversarial attack on YOLO. But it happens in other areas where you have, the machine has been working perfectly for 20 days, everyone's happy, one new image comes, nothing looks different, or one new environment, and suddenly you have 1,000 ROIs, or you have a lot of false alarms in one image, and you don't know why. People hate that. It's much worse than having an average stable number of mistakes per each image, okay? So that's, and the last one, well, like in chaos theory was talking about how a butterfly flutters its wings in Asia and it can create a hurricane somewhere. Well, if the image, with even very subtle changes, can get a different result, that's not a good sign, right? If the doctor says, these two images look the same to me, but the system says this is fine and this is cancer, that's very bad. Okay, so how do people, not just us, provide explainability right now? One mechanism, and there's a lot of papers about that, you can Google, that's an active area of research, is when you have discrete information, is to use some prominent factors. Say, we said we think you have pneumonia, mostly because of this factor, okay? That's a good way if you can do it. Another way, which is even cooler, harder, but cooler, is find similar past cases. Okay, that's a really good way, but it's very hard to do. A good example would be in medical area or in the legal area. Judges and doctors hate to be original. The best is they like that someone already had a case just like that, or many, and said, okay, the diagnosis is X, and they just have to apply it. They feel much safer that way. If you can find, and that's an example here, past nodules, cancerous or not, so actually you do know because they were already extracted, that look very similar in their important parameters to the one the doctor is looking at right now, that's a good, and you're saying, look, all of these were cancerous, we think they're similar, and that's why we think this one is cancerous. That helps them so much. Problem is, it's very hard to do. Like, there's no prescription how to do it. You have to figure out a way. Another way is to look at the path. This is actually, this slide, this part of that is not work done by NEC. We just use the similar mechanism. But basically, you do things like test time augmentation. For those who don't know, is basically you take the image or the scan or the data and you jiggle it a bit by adding some noise or doing some other things. And you see if the result changes, okay? So if the result changes because of small changes in the input, that's kind of a problem. Another example, which we actually did a paper on, is when to abstain. That is, when not to make a decision. Rather than explain your mistakes, how to know not to make a prediction when you see that the nearest labeled cases that you have in the last layer before the output are similar in some distance measure to the one. So you look at the most similar cases that you've had in the past in the similar output, and if you see they're all from the same class as the one you predict here, then you feel you're safe to make a prediction, regardless of what the prediction is. And if they're not, if they deviate, some say it's category A, some category B, you may not make this prediction. I want to get to a little more technical, so I'll just run. I'll just mention, in general, in science, people attribute the most value, and that's your customers as well, to something which is precise and explainable. Perhaps the biggest human victory of predicting something in the world is this parameter, which is the hydrogen energy levels. These three guys, Feynman, Tomonaga, and Schwinger, did it using QED. And that's a classic explanation, meaning they got the right number, and it's a result of a large series of calculations which gets better. That's real explainability. Explainability is not why something happened and we can't do anything about it. Explainability is, oh, we see we made a mistake here. This is the sample which looks like the most like it, and this is what we should do to make it better, like the next term for the precision. That's what customers want. An explanation that's just what it does, or some very lengthy explanation which you can't do anything about, that's not that great. So let's do a sandbox example. I'm not going to do full complex examples. That everyone here knows MNIST, right? Digits, handwritten, very simple. Okay, and we all know that it's very easy nowadays to get 99% and above with some very simple model with some data. It's very easy. It's a solved problem for all purposes. But assume now you do this for a customer and you mislabeled that 7 up there for some reason, and they say, look, well, we have some people writing like that, and that's important to me, and please improve that without degrading your other data, okay? So what you can do in order to reach an explanation in the meaningful sense is you can use things like augmentors, all kinds of tools. This is actually the name of a tool, but an augmentor is a description, so there's many augmentors, which takes your input and does some non-trivial things to it, okay? And you see how your output behaves. And then you might realize, and you say, okay, my explanation is that when I take this kind of 7 and I change it, we still don't identify it. It's not a one-off case. We just need more examples like that. So then, what are you going to do? Are you going to say to the customer, please give me more examples like that? If your customer is a city and you had a problem with a tandem bike, are you going to tell to the city, please get me more pictures? the whole situation is wrong, right? No one's going to do anything for you in the real world, okay? It's not a PhD student working for you that has to do it anyway. It's the real life, adult life. No one's going to do anything for you. And if there was an accident and you want more examples of accidents, in any case, it's going to take years. You got to have a generation method, okay, for your data. If you don't have that, you have nothing. I predict that in 5 years, the whole idea that a data scientist says, if you want me to get better, get me more data, it will be considered like not relevant to the discussion, okay? The data scientist is not that important. It's not, especially since people can do this. So what can you do? You can take an example of the 7 with this tip at the end, and you can use augmenters to generate more examples, or you can even make it draw it by hand. It doesn't matter, because you understood, or you think you understood, why we fail, because you need that tip at the end. And then you see how your system works. And if now you can handle all those cases, then your explanation is valid, and you solved the problem, which is the most important thing. And what the customer expects is that 1 year down the road, you will not make the same mistake, okay? That's progress, right? If there is no progress, generally being good is not going to cut it. I'm going to skip some of the slides. So I'm just going to flash this. I'm not going to have a lot of time to explain. If anyone's really interested, come to me later. But that's the most important part, actually, okay? We are proposing a definition for explainability, which is mathematical. The definition doesn't mean it's not a recipe. So we cannot explain in this way most of the problems. I don't know how to do it. My people don't know. Maybe we'll never know. But for some problems, we do. And what we're saying basically, and look at the graphics, the terms, the English and formulas are not useful. What we're saying is that if we have an explanation for the result of the system, if we can tie our answer and the sample you gave us to a previously labeled case in a path in image space or phase space where all the path is in the same class and all the operations are legal. Okay, I don't know how to say it faster, but basically, if this is 2 and this is the end of the animation is what we said is 2, then that's an explanation. By the way, it's also an explanation if we got it wrong. I mean, let's say we're given that, and actually you thought it's a 7 and we thought it's a 1, because you can get there. Then the explanation is wrong. I mean, we have an explanation why the system made this, but we made a mistake. But then we know how to fix this. I know it's a little complex, but it's simple to explain one-on-one. So anyone interested coming. We think that's actually quite major as a principle. And again, for most images or types of problems, we don't know how to do that. We actually are not sure that when you don't know how to do that, you really are going to have a system that does as well as humans. We're not sure. I'm not sure right now. I'm far less intelligent than some of the people doing research on ImageNet, but I'm not sure they know how to make ImageNet really better than humans in real life. I think there may be some very deep problems in there that no one has even discovered yet. And I'm not talking about adversarial attacks. I'm talking because you don't have this transformation there, okay? No one knows how to take one picture of a poodle and to transform it continuously into another poodle, the one that you saw right now, while keeping it a poodle all the way. That's the key thing. That's the hard thing. Okay, now, practical example. MNIST, everyone knows. Very practical example. I'm doing the 2D one because 3D is harder to display and to talk about. So retinal images, blood vessel segmentation. That's what an ophthalmologist does. Okay, they can segment it for us. And here you can see 3 different networks that were trained, and that's the colors. So when you see white, they all agree, and when you see a color, some of them disagree. Now let's look at some of the mistakes there. Look at the zoomed up areas. Now we're talking actual medical application. It's not much harder than the MNIST, but this is cutting edge, okay? People are deploying these right now and thinking about how to improve it. So you can see 2 mistakes here enlarged. One, the networks say the blood vessel is not continuous. See that? That never happens in real life. If it does, that's a terrible thing, okay? And here, they think they see some blood vessels, but they're none. And as people, we see that and we say, no, you don't need to be an expert. So why did they do that? Okay, when you look, now I'm going to give you the human explanation, which is very nice as an excuse or to soothe someone or to feel better about yourself, but that's not the solution, okay? So the human explanation is, okay, zoom in at the patches that the network actually sees, and you see that I hope that distance gives you the right. Do you see a line here and something which looks more like a line here? Do you see that? Great. So our eyes are very good at completing stuff. So the ophthalmologist says, sure, that's an eye. But if you look at the patch, this patch here, it doesn't look all that different from the patch upstairs. And that one is just a pot with no blood vessels. So when you look at it like the network looks at it, it's kind of hard. That's an explanation which may make me feel better about myself as a developer. Is it going to help the doctor? Not so much. So that's what people do. So that's the I can explain, okay? But that's not going to help us. What is a meaningful explanation? It's maybe not a nice explanation, but it's a meaningful one. I found an example where the ophthalmologist said there is no blood vessel, and using a series of legal transformations, meaning these transformations, the results in all the intermediate stages are still valid retina images. They look like retina images. And I found an example. By the way, when you look so close, I don't see what you guys see, but I remember looking at it, so I know it works. So you find an example which is very much like that. So what does this mean? It means that you can get to this sample from cases where there's no blood vessel. Okay, so now what is the solution? Either you change your mind, you say, you know what, actually there was a blood vessel there, then it's easy, you just mistaken labeling, no harm done. That's usually not the case. The other case is you have to generate more examples of this, which will not transgress to that region, okay? When you make data augmentation, you're not allowed to transgress too much, right? You took the 1 and you did 1 million augmentations and one of them took the line and made it into a 7, that's bad. But it's not so trivial when you're talking about serious augmentation to know what to do and what not to do. This tells you, in this case, this is the line. If you got to here, you're too far. Remake your augmentations and retrain. And when you do that, we're really short on time, then you find out that you only need 1 or 2 images, not 100. And you get the same result, the same quality with the augmentation as you get from using 100 images. And that's important because that's how people learn, and data aggregation for medical area is expensive and difficult, and there's privacy concerns and IPR. Doctors don't learn from looking at 1,000 images. They have a textbook. They have 1 or 2 examples, and then they train a little, and they know how to visually recognize a lot of stuff. Why can't networks do that? We're saying they can if you have the explainability model, if you can make the right augmentations. I'm going to skip about other things we do. I'll just mention that we're NEC, and NEC has 120 years of research. We're a bit older than IBM. We have the inventor of carbon nanotubes, still waiting for the Nobel. Jan LeCun, have you heard that name? He was a young guy in Princeton labs of NEC, and he had an idea to use something called neural networks to do face detection when people were still talking about Haar cascades and other things. And that's for YouTube. You can find a clip you can find on YouTube from 1993. So it took a while, but we are now a leading provider of vision analytics and biometrics, in a lot because of those early days. We do spaceships that have to do autonomously stuff in space because they're 40, 50, 1 hour, 1 light year away from us, and they have to land on an asteroid, which they just did. Hayabusa 2 did that and make some decisions. And we make accelerators for deep learning, which are based on vector processors. So it looks like a GPU card, but GPUs, basically you have in the card thousands of small processors. Here you have 60 or 100 vector processors, which are very long, good for long multiply accumulates, like 256 or more, which is something you need when you do 3D images and when you do fully connected networks. That's for the more technically inclined. If you have a fully connected layer of 1,000 and 1,000, GPUs don't scale well. These babies do. I'm going to skip the video. I'll just mention the center in Israel. I mentioned already, we're doing stuff in cyber with AI. We're doing the CT project and soon the other project in X-rays. We're doing edge AI, which means taking this stuff and putting it into the small chips which companies make, so you can do it in the area. That's what we did in cyber. NEC in general has a lot of computer vision applied. Not in retail, which is big. By the way, there's very few actual deep learning networks deployed in a commercial setting. We have been doing that before they were deep, and now we're using deep. That's an example of our system. Yeah, okay. I know there's lunch soon, but I did begin a few minutes before, so I'm going to steal 1 more minute. Oh, great. You see this lady, by the way? You see how she's crossing the street? The city may want to realize that, and we don't have money or time to have people actually label the images. So this pose estimation, or this, for example, that's a very sad case. That's the people who robbed a Holocaust survivor in Kfar Saba. The system doesn't understand the image, but it understands the skeleton. So you know something happened, people engage at close distance, and you ended up with man down, people running away. That's always a sign something bad happened. When you see man down and people running away, that's always a bad thing. You can see brawls. So in these examples, for example, you have to use augmentation, of course, to generate the data. You're not going to have some people give you all the data you want. This is another example, close-by encounters of 2 trucks. How likely is it that 2 trucks will be so close by and you'll get to measure it? So you have to simulate it. You have to simulate smear. You have to simulate rain or fog. This is our medical model. I'm at negative time, so anyone interested, you're welcome to contact me. I'll leave our email. I'll just show you, last thing, a short video about our AI in space, because AI in space together, that's really cool, right? Volume? No volume. So that spaceship, I asked about the volume. The Ryugu is a asteroid very far from Earth, and the spacecraft Hayabusa, which means Hayabusa 2, which means Falcon in Japanese, had to launch several micro rovers to land on it. One of them, by the way, has a CPU developed by Ramon Chips in Israel. And then we did another thing which is cool, shooting guns in space. Isn't that cool? We actually shot a projectile at 2 kilometers per second. You can see all the debris, and then we collected the debris. That's a good way to drill. We hope the asteroid is not offended. If space war happens in 2 years, it might have been because of that. We're very sorry. And I'm done. Thank you very much.